Okay, so now we can talk about lines and planes in space. So we've talked about dot products, we've talked about cross products, projections, work. So now we want to kind of take those types of topics and we want to expand on them in terms of different lines and planes in in the space. So most of the stuff we've been working with so far has been 2D. Now we're going to start mixing up into planes and lines, which is going to give us in the three-dimensional for XYZ plane instead of just our XY plane. These are going to be heavily used in the next course in Calculus 3, where we're in three dimension the entire semester. So the first thing we want to talk about is some parametric equations. So parametric equations of a line in space is given by a line L parallel to the vector V equals ABC and passing through the point P equals X1, Y1, Z1 is represented by the parametric equations x equals x1 plus a times t, y equals y1 plus bt, and z equals z1 plus ct. So if the direction numbers a, b, and c are all non-zero, then you can eliminate the parameter t to obtain symmetric equations of the line of x minus x1 divided by a equals y minus y1 divided by b and z minus z1 divided by c. So all of this is if we solved each one of these three equations for t. By solving each one of those for t, we can really say, in a sense, t equals every single one of those. Is really what we can kind of say. They're all symmetric equations, and we're going to kind of use that as we go forward. So the standard equation of a plane in space. So the plane containing the point x1, y1, z1 and having normal vector n equals abc can be represented by the standard form of the equation of a plane a times x minus x1 plus b times y minus y1 plus c times z minus z1 equals 0. By regrouping our terms a little bit, we can obtain the general form of the equation of a plane in space is given by ax plus by plus cz plus d equals 0. This is our general form of the equation of a plane. So given the general form of the equation of a plane, it's easy to find a normal vector to the plane. Simply use the coefficients of x, y, and z to write n equals abc. So I've written out all of our steps on this problem just because I want us to walk through every little piece of it. There's some extra words in here that kind of give us some hints and everything where I've typed them out. So I just wanted everything to be 100% clear here. So we're told find the general equation of the plane containing the points 2, 1, 1, 0, 4, 1, and negative 2, 1, 4. So it says to apply theorem 11.12, we need a point in the plane and a vector that is normal to the plane. So there are three choices for the point because we were given 3 points here, but no normal vector is given. So that means we're going to have to create our normal vector. So to obtain a normal vector, we want to use the cross product of vectors u and v extending from the point 2, 1, 1 to the points 0, 4, 1 and negative 2, 1, 4. So if we go back, we're starting at 2, 1, 1 right here. So we're going to start here and we're going to go to the other 2 points. So the component forms are, since we're going from those, it's going to be 0 minus 2, 4 minus 1, 1 minus 1. So if you remember from last section, we used an example that was very similar to this, where we had to find the area of the parallelogram, that had those. So that was our u vector. When we simplify, we get negative 2, 3, 0. V is negative 2 minus 2, 1 minus 1, and 4 minus 1. So we get negative 4, 0, 3. So we need to now find the cross product of our normal vector. So cross products of u and v, as defined here, ijk, negative 2, 3, 0, negative 4, 0, 3. So we're going to take our cross product here. So when we take the cross product, we get 9i plus 6j plus 12k. So if we kind of go back, we kind of fill in that gap. So we're going to have 3, 0, 0, 3 times I minus negative 2, 0, negative 4, 3 times j plus negative 2, 3, negative 4, 0 times k. So 9i minus 6, so plus 6j plus 12k. So that's where we get that. So therefore, our normal piece, now when we say ABC here, really what this is right here is saying 9, 6, 12. That's our normal. Our vector here is normal to the plane. So using the direction numbers for n, which is the 9, 6, 12, and the point that we were starting from, we started from the point 2, 1, 1. So you can determine the equation of the plane to be using this form right here. A times x minus x1 plus b times y minus y1 plus c times z minus z1 would give us our a, b, and c is 9, 6, 12. X1 is negative 2, or is 2. Excuse me. Y1's 1, z1 is 1. So 9 times x minus 2 plus 6 times y minus 1 plus 12 times z minus 1 equals 0. If we multiply all that out, we get 9x plus 6y plus 12z. Then we get minus 18 minus 6 minus 12, so minus 36 equals 0. If we were to divide everything by 3 in a simplified general form, we get 3x plus 2y plus 4z minus 12. So this would be the general form of the equation of our plane with that given information. Now, planes in space, they can be distinct, they can be the same, they can be intersecting, they can be parallel, they can be perpendicular, all different variations. So 2 distinct planes in 3 space either are parallel or intersect in a line. So if they intersect, you can determine the angle between them from the angle 0 less than or equal to theta less than or equal to pi over 2 between their normal vectors. So as shown in this figure. So notice our theta is down here. That's the angle we're trying to find between this plane and this plane. So to do that, we're going to have a normal vector of n1 because that's coming off of our elevated plane. And then n2 is coming off of our flat plane down here. So we need to figure out where we're at with that. So specifically, if vectors n1 and n2 are normal to their 2 intersecting planes, the angle theta between the normal vectors is equal to the angle between the 2 planes and is given by cosine of theta is equal to the magnitude or the determinant of n1 dot n2 divided by the magnitude of n1 magnitude of n2. So consequently here, 2 planes with normal vectors n1 and n2 are perpendicular if n1 dot n2 is 0, and they are parallel if n1 is a scalar multiple of n2. So we got 2 different things to kind of consider here. So considering 2 types of problems involving distance and space, finding the distance between a point and a plane, and finding the distance between a point and a line. So the distance d between a point Q and a plane is the length of the shortest line segment connecting Q to the plane, as shown in this figure. So that's really what we're looking at here. So the distance d between a point Q and the plane is simply the shortest line segment connecting Q to the plane. So that's what we have to kind of look at. We're trying to find shortest distances. So for any point P in the plane, you can find the distance by projecting the vector PQ onto the normal vector N. The length of this projection is the desired distance. So the distance between a plane and a point Q not in the plane is D equals the magnitude of the projection of PQ onto N, which is equal to the absolute value of PQ dot N divided by the magnitude of N, where P is a point in the plane and N is normal to the plane. So we got a nice formula that we can figure out distances with when we're talking space-wise now. So from this theorem, you can determine that the distance between the point Q of x0, y0, z0 and the plane given by ax plus by plus cz plus d is equal to 0 is d equals the absolute value of a times x0 minus x1 plus b times y0 minus y1 plus c times z0 minus z1, all divided by the square root of a squared plus b squared plus c squared. Or distance between a point and a plane, d equals the absolute value of x0 plus by0 plus c0 plus d, which is just simplifying this form right here, divided by that square root. So where P has the point x1, y1, z1 is a point in the plane, and D is equal to minus of ax1 plus by1 plus cz1. All right, so to find the distance between the point Q of 1, 5, negative 4 and the plane given by 3x minus y plus 2z equals 6. So to find our distance, we're going to use D equals the absolute value of 3 times 1 plus negative 1 times 5 plus 2 times negative 4. And our D is 6, so we need to do minus 6 all over the square root of 3 squared plus negative 1 squared plus 2 squared. So when we do that, we get absolute of 3 minus 5 minus 8 minus 6 over the square root of 14. So we get 11 minus 19 minus 16. So absolute of negative 16 over square root of 14, which reduces to 16 over the square root of 14, which is approximately 4.28. So we just got to kind of think about what we are doing here. So really we just did the dot product of our point and our normal line, which came from the 3, negative 1, 2 that they gave us. So the formula for the distance between a point and a line in space resembles that for the distance between a point and a plane, except that you replace the dot product with the length of the cross product and the normal in with a direction vector for the line. So the distance between a point Q and a line in space is given by D equals the magnitude of the line segment PQ cross U divided by the magnitude of U, where U is a direction vector for the line and P is a point on the line. So slightly different, but not much of a change. So in this case right here, it says find the distance between the point negative 4, 1, 3 and the plane given by negative 3x plus 2y plus z equals 1. So just like we just did, D equals the absolute value of negative 3 times negative 4 plus 2 times 1 plus 1 times 3 minus 1 all over the square root of negative 3 squared plus 2 squared plus 1 squared. So our distance D is equal to the absolute value of 12 plus 2 plus 3 minus 1 all over square root 14, which happens to be the exact same answer as the one before, which is 16 over the square root of 14, which is approximately 4.28. So we just got to kind of make sure that we're going about it the exact same way. and that we're able to compute things. So now we're told, find the distance between the parallel planes, x plus 2y minus 2z equals negative 2, and the plane given by x plus 2y minus 2z equals 1. So if we notice, both planes have a normal vector of I plus 2j minus 2k, so they are indeed parallel. So we know that because of the fact that n is equal to just our components, which is 1, 2, negative 2. And over here, n is equal to 1, 2, negative 2. So these two are equal. So to find the distance between them, we need to choose a point on the first plane and then find the distance from it to the second plane. Okay? So it means we're going to work with this one right here. I'm just going to pick an arbitrary point. I'm going to let y equals 0, z equals 0. So when I do that, x equals negative 2. So we now have a point, P, that is negative 2, 0, 0. And this is a point on the first plane. So then using the formula for the distance from the point to the plane, that's going to tell us d equals the absolute value of 1 times negative 2 plus 2 times 0 plus negative 2 times 0 minus 1, because that's the d from the second plane there, divided by the square root of 1 squared plus 2 squared plus negative 2 squared. So that gives us d equals the absolute value of negative 2 minus or plus 0 minus 1 all over square root of 9. So we get 3 over 3, which is equal to 1. So therefore, the distance between the parallel planes x plus 2y minus 2z equals negative 2, and the plane given by x plus 2y minus 2z equals 1 is 1. So now for this next example, we have that it says find the point of intersection of the plane x plus y minus z equals 6 and the line x plus 2 divided by 2 equals y minus 5 over 1, which is equal to z over 2. So first we need to convert the symmetric equations for the line to parametric form. So what we're really looking at is that, so the direction vector of the line is 2i plus j plus 2k. So to see that the direction vector, so in other words, first let's do it this way. Let's just kind of break this apart. T equals x plus 2 over 2. T equals y minus 5 over 1. T equals z over 2. So let's resolve for our x, y, and z. So 2t minus 2 equals x. T plus 5 equals y. 2t equals z. So if we remember back to our form that we know we have, so remembering back to our form here of x equals x1 plus at, y equals y1 plus bt, and z equals z1 plus ct. So we know that we have our vector v is our ABC, and our point is our p is our x1, y1, z1. So that tells us that we have our point P is negative 2, 5, 0, because that comes from this value, and there is no value here. And then we have that our normal is 2, 1, 2, because that comes from the values that are in front of our t's in each single case here. So to find the point on the line that also lies in the plane, we want to substitute the parametric equations for x, y, and z into the equation of the plane and solve for t. So, okay, so they gave us x plus y plus z equals 6. So if we have x plus y plus z equal, minus z equals 6. So that means we're going to have 2t minus 2 plus t plus 5 minus 2t equals 6. So we're going to have t, we're going to have minus 2, so plus 3 equals 6. So t equals 3. So it follows that the line intersects the plane when t equals 3 in the parametric equations. Thus, the required point is the following. So our point is the x, y, z point. That is going to be, we're going to plug it in for our z, for our values now, because really what we have here is 2t minus 2, comma, t plus 5, comma, 2t. So when we plug that t value in, we're going to get 6 minus 2, 3 plus 5, and 6, or 4, comma, 8, comma, 6. So this will be the point of intersection of the plane x plus y minus z equals 6 and the line x plus 2 over 2 equals y minus 5 over 1 equals z over 2. So you're seeing that we're starting to get more and more where these values are, or these problems are becoming more and more intense based off of what we're given and everything. So for this next one, we're told find the distance from the point P equals 5, 1, 4 and the line R of t equals 4 plus t times I plus 1 plus 2t times j plus 1 plus 2t times k. So the line R has the direction d of 1, 2, 2. In other words, our direction d is based off of the t terms. So it is 1, 2, 2. It contains the point of 4, 1, 1. Using the point that they gave us, so given P equals 5, 1, 4. So if we're going to denote this point that we found here, P0 as the 4, 1, 1. So then that means that if we find the projection P0 to P, so we're going to take P and we're going to subtract our P0 point. So this is going to be 5 minus 4, 1 minus 1, 4 minus 1. So we're going to get 1, 0, 3, which another way of writing this is I plus 3k. So the minimum distance between the point P and the line R is given by D equals the magnitude of P0 to P. So we want the magnitude there, times the sine of theta, which is really equal to the magnitude of P0P crossed with D divided by the magnitude of D, where theta is going to be the angle between the vectors P0P and D. So we need to find our top piece there. So P0 to P cross D is IJK and 103, because that's what we found here. And our D, which was way back up here, is 122. So this is 0322 times I minus 1312 times J plus 1012 times K, or in other words, minus 6I plus J plus 2K. So we need to calculate its magnitude now. So the magnitude of P0P crossed with D is the square root of negative 6 squared plus 1 squared plus 2 squared, which is the square root of 3641. Square root of 41. The magnitude of D is the square root of 1 squared plus 2 squared plus 2 squared, which is the square root of 9, which is 3. So therefore, D equals, in this case, because we're looking for this term right here now. So this is the magnitude of P0P crossed with D over the magnitude of D, which is the square root of 41 over 3. So a lot of this is just trying to figure out what in the world do we have going on? What are we looking for? And sometimes it is a little bit long, but it's nothing that we can't accomplish.